So for this example, we have that the average cost of a studio apartment in Fort Myers is $835 per month. The variable is normally distributed and the population standard deviation is $53. To see if the cost of rent has gone down, 37 tenants were asked their rent with an average of $809. At a level of significance alpha equals 1%, do we have enough evidence to support that claim? Okay, so for our first step, we want to verify that the conditions are met. I include this one here. As we get further, I may bunch it in with the others just because it's not entirely necessary at every single case. It's very, very important that you do this in the real world, but I'm not going to ask you very many trick questions where they don't work. I want you to get practice with this process, not get practice with gotcha problems. As long as you can recognize it, it's there, it's going to be there. Just be careful. But really, step one's for free. And then from there, we can move on to our second step, which is the first one that has a little bit of work, but not really that much. What we want to do is pull down our hypotheses along with our claim. So, pay close attention here to what is being claimed. Now, it is expressly stated that the average is $835 per month, but that is not the claim. That's just the assumption that we're always going to be working from, i.e. that's the null hypothesis. What we are claiming, or in particular, what is being asked about, in this case we say to see if the rent has gone down, we're kind of implicitly claiming from that question that we're looking for the potential that mu has decreased from $835. In particular, $835, but I'm not going to include the unit there, where this, as I said, is our claim. On the other hand, the opposite of this is that mu would be at least 835, where, again, reasonably our null hypothesis is that mu is equal to 835, but technically speaking, because we're looking to see if it's gone down, it going up would fill the same purpose of going against our claim. It would, again, provide evidence that doesn't support the claim. And then from here, we may want to be specific about what our null and alternative are in this context. The way I placed them kind of gave it away, but really, that's how it runs. And then once we have our hypotheses, we want to get our level of significance. Again, sometimes I squeeze steps 2 and 3 together because for our purposes, they're kind of free. In reality, again, steps 1, 2, and 3 are very, very important for us. They're kind of rote. But we're working, in this case, from alpha equals 1%. That value alpha is arbitrary, but we care very much. That's what it says, is we're willing to take at most a 1% chance that our result here isn't actually true if we're supporting our claim. That is, we're willing to take a 1% chance of rejecting the actual truth that the mean is $835. I don't know for sure, I haven't checked that recently, but that's what we're saying. That's what that 1% represents, is a 1% run at that value in particular. But that's where we're working, and then from there we actually get to do some math, where we want to find our test statistic, and bear in mind that, just to be sure, we are looking at a left-tailed test, because we're looking for things smaller than 835, but anyway, back to the math. We want to get our z-score here, our test statistic, which again, x bar minus mu over sigma root n. It's, again, that z-score that we're used to seeing from dealing with the central limit theorem and finding those standardized values. It's the exact same flavor of thing, essentially the same reason, it's just we have more context. But here, that would have the flavor 809 minus 835 over 53 divided by root 37, which would give us a value of about negative 2.98. And this is something that you can pay close attention to as you're getting more comfortable with these tests, that if you set this up wrong or if you look for the wrong thing, you'll notice that this type of value doesn't quite line up with the kind of test you want to run. Here we want a left-tailed test, and when we're talking about a z-value, we're talking about normalizing in terms of a mean, a standard mean of 0. So we should get a negative z-score, a negative test statistic. If we got a positive value, though, to indicate that we did our setup wrong somewhere and we might go back in there and check. But here, it's negative, it's as it should be. All is good so far. Then, once we have all of our pieces, well, we need to find our comparison value. We need to find what we're actually going to be working with here. We need to find the value that we're running our test in terms of, which, in this case, is going to be a p-value that we can get from a table if we want, or we can get it from the normal CDF function. Actually, with this class, with this section, you can do everything in terms of functions you've seen before. It's just very slow. Or you can introduce yourself to a new function in the calculator called the z-test function. We're going to be doing a lot with these testing functions in the calculator from now on, where that will get you, among other things, the p-value we're looking for in this case, which would be a value of 0.0014 with associated distribution pictured. And as a result, thinking in terms of that p-value and that z-score here, p.0014, on that distribution very far into that left tail, but in particular, it is far enough to be below 1% or alpha. My alphas keep turning into deltas. Or that's not delta. I can't remember what Greek letter that is, but it doesn't look like alpha either. Point is, this value is smaller than that value. P is low. So, as we say, we will reject HO. Again, small p-value means you reject the null hypothesis. That is, we get a value so small that it corresponds to a great deal of unlikelihood. That is, the mean we got from our sample of 809 is so incredibly unlikely if we assume it should have been 835 with the given sample that we had, with the given standard deviation that we expected, that we can say with some certainty, with a great deal of certainty, in fact, that there's something wrong with our assumption, because the likelihood of this happening was less than 0.1%. Very small. Well, not less than 1/10. About 1/10. Close enough. Point is, it's incredibly unlikely, and that's what we want to see if we want to reject the null hypothesis. But more importantly, this is the type of thing we're looking for here. Where another way that you can pay attention as you're getting comfortable for errors is if you get a p-value that's really, really large, it probably means something went wrong as well. Maybe you looked for a right tail instead of a left tail by accident. That does happen. But in this case, p is lower than alpha, so you reject the null hypothesis. And as a result, when you want to interpret your result, you would say something to the effect of, there is enough evidence at level of significance alpha equals 1% to support the claim that the mean cost of rent is less than $835. Now from here, I have another example for us to go through. We're going to look at this same kind of process, maybe with a little bit less detail, but just understand that as we're doing this, you really want to get comfortable with that z-test function of the calculator, or Excel methods, or online methods, as that's the most efficient way to do this kind of problem. We're going to see ways to do this with other things. We're going to see other options. We're also going to see stuff with critical values as well, just to be sure. But you really, really want to get comfortable doing the basic work in the calculator, because you're going to be doing this fairly often, and it pays to be efficient. Anyway, as we're working, we're going to do one more example here with this same type of setup.